Hello, Mr. Simpson here with our video for Chapter 11, Section 4, Colligative Properties. As always, here are the learning objectives for this unit, so please pause your video now and copy these in your notes. All right, so let's start with a discussion about what is a colligative property. So properties of solutions are very different from those of pure solvents, and some of these differences are based on the identity of the solute. Some only depend on the concentration, not the identity. We're going to focus in on colligative properties, which depend primarily on the concentration, not the identity or the nature of the solute. So here are the four colligative properties that we are going to cover in this unit: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Now you can probably tell by the names of those how the property for the solution is going to be different than for the pure solvent. So vapor pressure lowering tells us the vapor pressure of the solution will be lower than the vapor pressure of a pure solvent. Boiling point elevation, the boiling point of a solution will be higher than the boiling point of a pure solvent, and so on. We will spend a good portion of this video going into more detail in these four different colligative properties. Before we get to that, though, I do want to talk about because colligative properties are affected by the concentration and not what the particles are. Concentration will be important in a second here, and actually at the bottom here, you can see four different ways in which we will be looking at concentrations. Some of these we have seen before, some of them will be new. Additionally, we have to take into account something that's known as the Van Hoff factor, right here, the Van Hoff factor. And so this may make some sense to us after just talking about electrolytes and the idea that a strong electrolyte occurs because you get a complete dissociation of positives and negative ions from an ionic compound. And a non-electrolyte would be an example of a molecule or covalently bonded compound dissolving. You would not get that separation of positives and minus and negative ions. So we need to take that into account since we're talking about concentration here. This idea that when a molecule dissolves in solution, so if something like a sugar like glucose was the solute in our solution, well, for every 1 mole of glucose, I'm getting 1 mole of particles. All right, so that is not going to separate out into other parts. It's just we're going to get that 1-to-1 ratio. However, if I have an electrolyte, an ionic compound, for example, when 1 mole of sodium chloride dissolves, I'm actually then producing 2 moles of particles. Those 2 moles being, as you know, are sodium ion and our chloride ion. All right, so that needs to be taken into account in some of our colligative property calculations, which we'll get to in this video. So you can see, for an example here, that Van Hoff factor, which is again represented by lowercase I, if my solute was sodium chloride, I'd have to use a 2 there. If it were a molecule or just an atom, from the periodic table, then my Van Hoff factor would just be 1. That's not going to apply to every colligative property, but you will see when I introduce the formulas where it does take place. Okay, before we get into the individual colligative properties, let me talk for a quick moment about the different concentrations that we're going to see with these various colligative properties. Okay, molarity is the first one. You may recall molarity is moles of solute over liters of solution. All right. If you're lucky, the problem will give you the molarity, but we should go in being prepared to have to calculate molarity. And again, they're probably not going to give us moles of solute. They're probably going to give us the data that was used to make that solution, so we should expect to be given more often than not grams of solutes, okay? And then have to do a conversion to get to moles before I plug it in with the volume of the solution to get my molarity. Mass percent is exactly how it sounds. Mass percent is part over whole, so it's the mass of the part over total mass. And since it's a percentage, we'll multiply it by 100. Okay, the reason why I'm not distinguishing here between solute or solvent or solution is because it could be either. They could be asking the mass percent of the solutes or the solvent. So it's the part over the total, part over whole times 100 to get a percentage. Mole fraction is next. Mole fraction is very similar to mass percent, but it'll be in moles instead of grams, and it'll just be left as a fraction. You will not multiply it by 100 to make it a percent. The symbol for mole fraction is X, and then we put the symbol for whatever. So if I was doing the mole fraction of water, I would write it like this. Okay, then it would be moles of part over total moles. Okay, this could be the mole fraction of the solute or the solvent, or a particular in a bigger solution, a particular compound or molecule in that solution. But it's the moles of whatever it is. In this case, it would be the H2O. So I would have moles of part here would be moles of H2O if I was doing the mole fraction of H2O over the total moles of the solution. All right, and finally we have molality. Oh, that is a typo, my fault. Molality as our fourth concentration unit. Notice the difference here. Molarity is a capital N, molality is a lowercase m. And molality's formula is moles of solute over kilograms of solvent. Moles of solute over kilograms of solvent. Again, we may have to do some conversions to get to those values before we plug them in to get our molality. All right, I'm going to pause it there. Please pause it there. Make sure you have these equations down to calculate these various concentration units. All right, so let's get into each of the colligative properties at this point. So the first one is vapor pressure lowering. So you can see in the flask on the left, we have pure water. We have spent a good amount of time talking about where vapor pressure comes from, so I'm not going to go back into that. You have the videos in your notes. But so the question here is what happens between a pure solvent and then when I add a solute. So you can see what happens here. Once the solute particles are in the mix, they actually physically are blocking the ability for those solvent particles to escape to the gaseous phase. So the result is you'll have fewer gas molecules in the gas phase above the surface of the liquid. So if I have fewer gas molecules, what happens to the pressure? The pressure would decrease. Okay, so the vapor pressure of a solution is less than the vapor pressure of a pure solvent. All right, we can look at this mathematically using Raoult's law. Okay, there's the equation for Raoult's law. You can see that it's the vapor pressure of the solvent in the solution. It's the mole fraction. So all of these colligative properties are going to have some sort of concentration as part of it. In this case, for vapor pressure lowering, Raoult's law, we're going to deal with mole fraction. Okay, and then the vapor pressure of the pure solvent. Take a second and copy this problem in your notes, and then I will work through it with you. All right, let's work this practice problem here. Okay, so we know our formula. Is this. Okay, so let's see what the problem gives us. It's asking for the vapor pressure of the ideal solution. So what is the vapor pressure of this solution? So that means we are looking to solve for this value here. That means I need a vapor pressure of the solvent, and I need the mole fraction of the solvent. Pure ethanol, which is the solvent, has a vapor pressure of 1.078 atm. Okay, so That's good. I know that this value is 1.78 ATM. Okay, now I need a mole fraction of the ethanol. All right, and you can see they've given me grams of both values. Okay, so here's where that conversion work comes in. Luckily for us, we've done quite a bit of this. So over here on the side, I'm going to take my 92.1 grams of the glycerine, and I'm going to convert that to moles. I'm going to look up that molar mass, and I'm going to get here a value of, I'll write it just down here, 1.00 moles of glycerine. All right, do the same thing for the 184.4 grams of ethanol. My molar mass here is 46.07 grams, and I'll get a value here of 4. Nice, neat numbers here for us. Won't always be the case, but for this example, pretty straightforward. Okay, so I need that mole fraction. So I need the mole fraction of the solvent. So I need the mole fraction of the C2H5OH, which means it's the moles of C2H5OH, moles of the part, in this case the solvent, the ethanol, over the total moles. All right, and I'll get a value here of 0.800. No units there, don't worry about the units. So now I can plug this value in here, and I will get a new vapor pressure for the solution of 0.142 ATM. All right, always make sure your answers make sense. So the pure solvent was 1.78, the solution is 1.42. The name of the colligative property is vapor pressure lowering, so that value does make sense. All right, I'm going to group the next two together because they're very similar. Boiling point elevation, freezing point depression. So these are properties you're a little more familiar with, and properties that have an impact on our everyday life. Freezing point depression is a big one, right? Coming out of the winter, when snow and ice falls in the roads, the road crews get out there and put salt on the roads, and the goal there is to lower the freezing point of the water that's falling on the road so that it doesn't freeze. All right, so you will see here that vapor pressure lowering did not need to account, because we're doing the mole fraction, did not need to account for the Van Hoff factor. But these two do. You'll see that's in there. So I have to think for a second about what my solute is and if I need to include something other than 1 for my Van Hoff factor. Okay. Additionally, this lowercase m, if you'll remember, is molality. All right. So in both cases, we have molality. Obviously, these values are change in boiling point temperature, change in freezing point temperature, and then you'll see here we have two constants which are referenced here, the boiling point elevation constant and the freezing point depression constant. Okay, now one quick note here that you're calculating the change, you're not calculating the new boiling point or new freezing point temperature. Okay, so if the question is asking for the temperature, you need to add the change, right, because it's boiling point elevation, so the solution's boiling point will be higher, or you need to subtract the change in freezing point because it's freezing point depression. Okay, go ahead and pause the video for a second to copy down this problem. Okay, so as I take a look here, find the boiling point of a solution. All right, so that tells me I need this equation here. All right. That means I need a KB value. This is a value you would look up. There's a table in your in the PowerPoint and in the book, and actually the solvent is chloroform, right? In chloroform, so that's the solvent. So if I looked up these values for chloroform, I would find the KB of chloroform is 3.63, and the normal boiling point temperature of chloroform is 61.26 degrees Celsius. All right, that'll be important. If it were water, I wouldn't I wouldn't have to look up the boiling point temperature of water. We would assume it was 100 degrees Celsius, but you would need to be able to look up that constant. Okay, so now back to our problem. So I know the KB value is 3.63. If I'm lucky, they'll just go ahead and give me a molality right in this problem. And you can see they have not done that. They've given me 92.1 grams of iodine and 800 grams of chloroform. Now, this is where sometimes students get a little lost, right? Because they've given me 2 gram values, one of which I have to convert to moles because it's the solute, the thing being dissolved. The other I need to convert to kilograms because it's the solvent. So if you remember, molarity equals moles of solute over kilograms of solvent. Okay. Typically, the larger one is the solvent. We know water is the universal solvent. Sometimes also the wording. Find the boiling point of a solution of 92.1 grams of iodine in. So because it says in 800 grams, that's my clue that the iodine is the solute and the chloroform is the solvent. Okay, so we need to do a couple conversions here. Let's convert the grams of iodine to moles of iodine. I will calculate the formula mass of iodine, 253.81 grams per 1 mole, and I get 0.363 moles of iodine. I also need to do my 800.0 grams of chloroform doesn't work, but this is just a metric conversion, right? So 1 kilogram is 1,000 grams. I get 0.8000 kilograms. All right, so now I have the values I need to go ahead and plug in here to solve for molality. So I get 0.363 moles of iodine over 0.8000 kilograms, and I get a molality value. Here of 0.454. All right, and then just lowercase m is the symbol for molality. Now that I have that, I can bring out here and plug that into my boiling point elevation, and I get a change in boiling point of 1.65 degrees Celsius. Now, if it asked for the change in boiling point, I would be done there. But since it's asking for the boiling point, I need to take the 61.26 degrees Celsius, add that change because it's boiling point elevation, and so 1.65 degrees Celsius, and I get a new boiling point of 62.91 degrees Celsius. Again, right here, if this were a freezing point problem, I would be subtracting the change from the normal freezing point of the solvent because it's freezing point depression. All right, one more colligative property cover here, and it's osmotic pressure, osmosis. So semipermeable membranes allow certain molecules to pass through, and based on size, shape, and other factors. So the transfer of solvent molecules through a semipermeable membrane is osmosis. So for example here, if you take a look, we have pure solvent on one side, a solution on the other, and they're separated by a semipermeable membrane. Well, it's going to be easier for the solvent to pass through that semipermeable membrane than the solution with the larger solute particles dissolved in there. So what happens is the level increases on this side, and what the result is our osmotic pressure. Okay, the flow of solvent during osmosis creates a force. That force is the force necessary to prevent osmosis from occurring is osmotic pressure. Okay, here's the symbol for osmotic pressure and the formula. You will see once again that because concentration here, this time we're going to deal with molarity, and the Van Hoff factor is once again in play if we have an ionic compound that needs to have something other than 1. Okay. Again, the concentration we're using is molarity, and you'll see that we have the gas law constant of R and the temperature of T. Now, because the gas law constant has a unit that is liter atmosphere mole Kelvin, that means our temperature needs to be in Kelvin. So be aware of that as I take a look at some problems. I have a problem here for us to try, so why don't you go ahead and pause the video and copy that in your notes. All right, so what is the osmotic pressure is the question here. So I know that means I'm using this formula. Okay, the solute is glucose, so it is a non-ionic compound. So I know that means the Van Hoff factor is not going to be in play for us here, just like the boiling point elevation problem I showed you a second ago. So that means we need a molarity, a gas constant, and a temperature. Okay, so I always know this value. This is our gas constant. And again, be careful of your units, liter, atmosphere, mole, Kelvin. Sorry, it's hard to see. That means that I need a molarity, and this doesn't always happen, so enjoy it when it does. They actually give me the molarity, so I can just plug that right in. As we have seen already in some problems, we should be prepared to have to calculate molarity before plugging it into this equation. We do, however, need to deal with the temperatures in 37 degrees Celsius, so that means I need to add 273.15, and I get a temperature in Kelvin. All right, so pretty straightforward here, and I get an osmotic pressure of 7.6 atm. Okay, so lots of different types of calculations in this colligative property units. In addition to the new equations we've given you for osmotic pressure, boiling point elevation, and freezing point depression, and Raoult's law, there's also some calculations that will often need to be done before solving these equations, which are the solving for these different concentration units. Okay, so lots of practice ahead as we continue to cover colligative properties.